All right, my algebra kids have a quiz coming up over some things about systems, solving some word problems, solving some 3x3 systems, and then systems of linear inequalities. Now I've got a video that I will link about how to graph linear inequalities. It's one of my favorite videos that I made. So hopefully that'll help you how to graph one of them. Today we'll be graphing two, so let's get right to this. I gave all my students this practice quiz so that they could know what was coming here shortly. So hopefully this will help going through. So this first problem is a classic type problem where it is coins in a jar. So there are 35 coins in a pocket or jar, all of which are quarters and nickels. So that's clue number one. And then clue number two will get us equation number two. If the total value of his money in his pocket is $3.95, what does he have? He's only got quarters and nickels. So let's go ahead and dig right into this. So we're going to have Q will be the number of quarters. N will be the number of nickels. And we'll go from there. So the number of nickels plus the number of quarters is what? How many coins are in the pocket? 35. Now, the first equation always deals with the number of coins, okay? And then the second equation that I'm going to write down here will be dealing with the money, or how it all adds up. So 5 cents for every nickel plus 25 cents for every quarter totals how much? And you might be saying $3.95. But wait, that doesn't make sense. Get it? It doesn't make sense. This is cents, this is cents, so we have to make sense of the right side. I know it's a really bad dad joke, but there you go. That's what I do. $3.95 on the right side. Now you could go to Desmos and graph those and find the point of intersection, but for purposes of the quiz, I might not let you use Desmos. So we got to remember how to do the elimination method. I'm going to multiply the first equation here by -5. And the reason I'm doing that is because I see if I do that, the ends will eliminate. It's called the elimination method or linear combination. I'm going to multiply everything by -5, so -5q equals, and we take our handy dandy calculator here, and we take 35 times 5, which is 175. It should be negative. We then add the two equations together. That's part of what the elimination method is. 20q equals 220. So q equals 11 quarters. 11 quarters. So how many nickels then? Well, 35 minus 11 equals what? 24. So 24 nickels. Now you could go through and add up the money, and I can pretty much guarantee that it will add up to $3.95. So that's how you do the problems with coins in a jar and money. All right, number two is similar, but I wrote it in such a way that it's a little bit different. We're going to use the substitution method on this one. A 5th grade class went to the ballet to see the Nutcracker. There were 15 more children than adults. That makes sense. It would kind of be silly if there were more adults than children, right? With a total paid admission, so if you add up all the money, it totals $207. The adult ticket, 15, children paid 9. Who went to the ballet? How many? There's only one possible combination there, one possible solution. So the number, let's first add up the money actually on this one. So 15 times the number of adults plus 9 times the number of children, that all adds up to $207 total. Now, I made this problem hopefully interesting, I don't know, because it says there were 15 more adults than children. 15 more children than adults. So let's just translate that. I call it translating, like you translate into a different language. We're translating English into algebra. The number of children are, right, that's your equal sign, 15 more than the number of adults. There were 15 more children than adults. So the number of children is 15 more than the number of adults. So the substitution method, and I have plenty of videos on this also, is where you sub one player out of the game and you put an equal in there. Equal player goes into the game, and then you're able to eliminate a variable that way. So 15a plus, sorry, I'm trying to go too quickly here, I think. Let me back up. You're probably screaming at your computer here. So C is right here. So we're going to put that right in there. So 15a plus 9, 15 plus a. The reason I knew I had done it wrong was because I was going to get another equation with two variables, and that was going to be unsolvable. So I wanted to eliminate one of the variables. So yeah, I had to go back and look. So this is 135 plus 9a plus 15a equals 207. Then you just solve this. These guys are on the same side, 24a. And then I could subtract 135 to the other side. So I'll go to my handy-dandy calculator, 207 minus 135, and I get 72. So A equals 3. 3 adults. I'm glad that worked out. So that must mean the number of children are plus 15. You get 18 children. And you can add up the money. It should add up to $207. So there's the word problems using 2-by-2 systems, 2 variables, 2 unknowns, or 2 variables, 2 equations. What about a 3-by-3 system? I'm going to put one of these on the quiz. I'll try to make it relatively simple. This is probably a little harder actually than the one on the quiz. The idea here is to whittle it away and get rid of variables as you can. So I'm looking at this and I notice these guys right here that if only one of them had been negative, I would be in good shape. So what I'm going to do is actually change the signs on the middle one, and then I'm going to combine these. And when I combine them, I get negative or positive 1y plus 2z is 8. All right, now listen carefully. That's great, right? I got rid of a variable. But I still have y and z. What do? I have to go back to my original ones, and I have to use equation 1 because I haven't used it yet. I have to use equation 1. And I also have to come up with a plan to get rid of the 2x so that I have another yz combination. So what I'm going to do, I'm going to multiply my equation on line 2 that has the negative x there. I'm just going to double it and write it in blue up top. So negative 2x minus 4y minus 2z is negative 22. Right? Does that make sense? Now I'm going to add these two and I'm going to write it down below. Okay, so I'm adding those two because I see the x's are going to eliminate. Negative 3y minus z is negative 9. All right, so you might want to pause the video and look and see what I did there. I got rid of x in 2 different ways so that I now have 2 yz equations. Now I just focus in on this as though it's a new problem. And what I'm going to do is rewrite the first equation. I'm not going to change it at all. I love using colors on these. I think it helps you see what I'm doing. So I didn't change anything with the first equation. I am going to double this one. I'm going to multiply by 2. How did I get that? Well, I saw that if I double the second equation, the z's will then match. Positive 2, negative 2. It's going to add up to 0. So I add them up. I get negative 5y equals negative 10. Y equals 2. Aha! 2. I can put it over here on the blank. Thank the Lord, I got one of them. All right. Y equals 2. Now what? That's the hardest thing, is getting the first one. What you do is you go back to one of your 2 by 2 equations. It doesn't matter which one. I'll take the first one, my red one, and I'm going to put my answer in there. I just found out that y is 3. So 3 plus 2z is 8. I subtract 3. All right, so what did I do wrong here? Y is, I put y over here first of all, 2. Oh, y is 2. So I put a 2 in there. That's a 2. So then I subtract 2 on both sides. I get 2z equals 6. Z equals 3. So z equals 3. Now, where do we solve for x? The only place x's are in the original equations. So I'm going to take one of my original equations, pick your favorite one, whichever one you think would be easiest to work with, and you plug your 2 in here for y. You plug your 3 in for z. I'm trying to be more careful this time so I don't embarrass myself and make another mistake. X plus 6 plus 9 is 19. This is 15. So if I subtract 15 on both sides, I get x is 4. Hallelujah. And you can go in and plug in those 3 numbers to all 3 of the original problems, and that combination will work. So that's pretty darn cool. So that's a 3 by 3 system with several transformations that I had to do. The last section in our chapter had to do with systems of linear inequalities. I put here on the quiz, be sure to shade, and the reason I put that there is you wouldn't believe the number of students who just draw the 2 lines and they stop. They're missing the entire point of this. It is shaded regions. So again, I will use colors to my advantage. Hopefully that'll help you see. So what you do is you graph the boundary line, y equals negative 2/3 x minus 3. So you go down 3, put a dot. I got plenty of y equals mx plus videos on my channel. We go down to, always go right if you want to be right. And most of you think you're always right, right? So always go to the right. Oops, I didn't quite go far enough there. All right, and then I draw a solid line. And the reason I'm drawing a solid line is because it has the little bar there. Okay, that's like the closed circle concept back in one-dimensional inequalities, like y is greater than or equal to 3. We do a closed circle. Now, because it's a greater than, and it says y is greater than the line, we shade above where all the big y's are. See, this is where y is really big. I think this is how my brain works, at least. Y is bigger than the line, so I shade above. There we go. Okay. Now, the second equation is right here. I'll do this one in blue. I go up 2 and put a dot, and then I go up 3 over 5. Down 3, back 5. Again, I don't really care where the lines hit this time. I really don't. And I draw a dotted line. It's all about the shaded regions here. I'm doing a dotted line because it does not have the equal sign there. I get that question so many times. Dotted line, same as an open circle. It doesn't have the equal, okay? Since it's a less than, where are the y's small? The y's are small underneath, so I shade down here. And then the answer region is the highlighted region. So in here, this is where the solutions are. Everything in that region. So if I asked you, is 5, 3 a solution? Yes, it is. It's in that really ugly color, whatever the heck that is. All right, really quickly, let's do the next one. And this is the last one on my quiz review and in this video. So hopefully you will have found this helpful. Okay, let's So the first one will go up 2, put a dot. We're going to go up 2 over 1, up 2 over 1, down 2, back 1. And I'm going to do a solid line through that. Now this is a less than symbol, so y is smaller than the line. That means we shade under. What about the other one? It is a wee bit different, but you know what? We can find our happy place by subtracting x on both sides. Notice I wrote it in y equals mx plus b form, so m is -1. So I'm going to go up 3, put a dot, and then I'm going to go down 1 over 1. And I do my dotted line through that, and then it does have a less than sign, so I am going to shade. I'm not going to shade in ugly black. I'll use this ugly green. And I will shade it down, and then let me just accent. This is where all the solution region is down below there. So they were both shaded below, which created this wedge shaped in the bottom area. All right, well, hopefully you found this video useful, and now you're ready to just kill it on the quiz that's tomorrow. And maybe you're not in my class, but still, maybe this was helpful to you. All right, well, until next time.